This is chapter number 5, Laws of Motion. Newton's third law of motion. What did the second law says? It says force is directly proportional to acceleration and mass. Okay. So the external force on the body causes certain acceleration. From where does this external force act? What is the origin of this external force? What is the agency which is providing this external force? When we talk about Newtonian mechanics, the external force is arising due to some other system or body. If you consider two bodies, say A and B, then B gives rise to external force on A. Now the question arises, does A in turn give rise to an external force on B? That is, if this is A, this is B. If A is giving some force or thrust to B, what is B giving to A? If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts some force on your hand and you can feel it easily. But what when they are not in contact? Bodies are not in contact. For example, earth, it pulls anything downward due to gravity. Now what is stone doing with earth? Means if this is earth, there is a stone or any other body. Now earth has a tendency to bring the item back, body back, because there is a gravity. Center of the earth has some gravitational pull. Now when it falls or when it is falling, does this stone also provide or gives some or resultant force on this earth? The answer is yes. And what is that force? We can't feel it. The mass of this body is very less. This stone is negligible as compared to the mass of earth. So we don't feel it. According to Newtonian mechanics, force never occurs singly in nature. These are two bodies. So the force is the mutual interaction between these two bodies. In other words, we can say that force always occur in pairs. And the mutual forces between two bodies, they are always equal and opposite. And this idea is expressed by Newton in the form of third law of motion. That says to every action, there will be always an equal and opposite reaction. So this is quite crisp. This line is very crisp, very beautiful also. And in common language, we can say like this. But because of this simple line, there may be some misconceptions. We need to, point out certain important facts about the third law. What is action? What is reaction, especially? So the term action and reaction in the third law means nothing else but the force. Action, reaction means force. We can use different concepts, but that will be confusing. So we'll stick to the force. A better way to state the third law will be force always occur in pairs. So force on body A by body B is equal and opposite to the force on body B by body A. The action and reaction pair in third law, they may give some wrong impression that action comes before reaction. Action is the cause. And reaction would be the effect. So there is no cause-effect relationship implied by the third law. And the force by A on B or A by B and the force on B by A, they would act at the same instant. In the same reasoning, any one of them can be called action and reaction. So action and the reaction forces, that is FAB, force on A by B, and they act on different bodies, not on the same body. So these are two pairs, A and B. So this is A by B, force on A by B, and this is force on B by A. So if we are considering the motion of any object, say A or B, only one of these two forces may be relevant. It would be an error to add up these two forces, and we can not claim that the addition of these two is 0. But when you are talking about a system as a whole, means this is for this scenario, it is not acceptable. But when we are considering a system that is two bodies as a whole, that is FAB and FBA are the internal force which are acting on a system A plus B, both the bodies are involved, means you consider them as a system. Now they add up to give a null force, and internal forces in a body of a system of particle, they will cancel away in pairs, and this will be very important. We'll see in next discussion also, and solving the questions also. Let us take an example. Two identical billiard balls strike a rigid wall with the same speed but different angles, one like this and one with certain angle. What is the direction of the force on the wall due to each ball? What will be the force? And the ratio of the magnitude of impulses imparted to the balls by the wall. So what will be the force imparted or applied in result to the ball striking it? And we'll use see, the very intuitive answer will be, might be the force on the wall will be normal to the wall like this, and in this case it is inclined at say 30 degree. This is 30 degree, but this intuition may be wrong. The forces on the wall is normal to the wall in both the cases, so they will be normal, means perpendicular, this perpendicular, this perpendicular, so they will be, in both the cases they will be normal to the wall. So how we are going to find out the force on the wall? There is a trick. We'll consider the force or the impulse on the ball due to the wall using the second law, and then we'll use the third law. Means, let us say that u is the speed of each ball before and after collision, because the speed is not changing, and m is the mass of the ball. Say m is the mass of each ball. Now we will consider axis as given in this figure, and also consider the change in momentum of each ball. In this case, first, if this is u, this is m, initial momentum is m into u, then this strikes the wall and comes back, returns back. So the velocity first it was in this direction, then it will be in opposite direction. So the px in this case will be this direction, py is 0 because this is normal to the wall. So mu and then return minus mu. So this is px initial, px final, and the py in both the case will be 0 because this is normal, perpendicular to, if you can find it, the cos theta, u cos theta, u sin theta, you will find out that ultimately the y component is going to be 0 because of the cos component or the theta component. Now impulse is what? It is the change in the momentum vector. So mu, this is the resultant, minus mu minus of mu, that is minus of mu minus mu, and that will give you minus 2 mu, and if you add these two, that will be 0. So y component will be 0, and in this case the impulse and force are in the same direction. The force on the ball due to the wall is normal to the wall because it is not going anywhere, and this will be along this negative x direction. As you see here, the sign is also showing that. And if you use the Newton's third law of motion, the force on the wall due to the ball is normal to the wall, that is in the positive x direction, right? The magnitude of force we cannot ascertain since the small time is taken for the collision, and which is not specified in the problem, so we'll leave it at that. Now let us come to the second part. it is striking and coming back like this. So this is the direction and this is the direction. So what will be the px initial? That will be mu cos theta. See, if I make this as cos theta and this as sin theta, this is theta, the direction is like this. So what will be the px? Always, if you have any direction like this, x component is this and y component is this. In this case, we have x component and this is what the y component. So x component will be mu cos theta and y component will be minus mu sin theta, right? In this case, px final, it is going like this. So what will be the x component, which will be again, because in this case, if this you take cos theta in this direction as plus, in this case you have to take it as negative, right? Because in this case the cos is like this, in this case the cos is like this, so it will be minus mu cos theta. But the y component remains the same for both of these, okay? So it will be minus mu sin theta and this will be minus mu sin theta. Now this px, the x component is changing sign after collision. See, mu sin theta and this is minus mu sin theta, while this is not changing. Now what will be the x component of impulse? Mu cos theta minus of mu cos theta, that is minus 2 mu cos theta. And when you add these two, means minus mu sin theta, not add, we have to subtract. Minus mu sin theta minus of minus mu sin theta, that will be plus mu sin theta, these two cancels out and y component will be 0. So the direction of impulse in this case is, as we saw, it will be the normal to the wall along the negative x direction. And using the Newton third law, we'll find out the force due to the ball, which is normal to the wall along positive x direction, and the ratio of magnitudes will be, previously what it came, it was this value, then we got this value. Divide 2 mu by, rather minus sign will be cancelled, so 2 mu by 2 mu cos 30 degree, which will be 2 by root 3, which comes to 1.2. Conservation of momentum. There is an important result or consequence of the second and third law. This is the law of conservation of momentum. Just consider a bullet being fired from a gun. So if the force on the bullet by the gun is F, the force on the gun by the bullet will be what? It is a recoil. It will be minus F. Bullet will, see, if the bullet goes like this, there will be a recoil in the opposite direction. So if this is F, this would be minus F, according to the third law of motion. And the two forces are acting on common interval of time, that is delta t, same. So what is the second law, which is F? This delta t is the change in the momentum of the bullet, F delta t for this one, same time, and minus F delta t is the change in the momentum of the gun. And since both are at the rest, the change in the momentum equal to the final momentum for each. If Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, that is mass into velocity, that is F into delta t also. So Pg will be equal to minus Pb by this discussion, they are opposite. Take this on the left hand side, Pb plus Pg will be 0. So total momentum of the, that is bullet plus gun, will be conserved. So when we say an isolated system, that is the system which has zero or no external force, the mutual forces between pairs of particles in the system, this can cause momentum change in the individual particles. But since the mutual forces of each pair are equal and opposite, the momentum changes cancel in pair. That is why the total momentum remains unchanged. And this is the law of conservation of momentum. So the total momentum of an isolated system of interacting particles is conserved. Let us take an example. Collision of two bodies. When two bodies are colliding like this, this is coming from this side, this is coming from this side, and they get apart now. They are initially like this, then they collide and this is in this direction, then it goes in another directions. So if we have A and B, these two bodies are there. The initial momentum, which is PA and PB, so PA here, PB here, and the final momentum, say it will be PA dash and PB dash. And by the second law, we know that F A on B into delta T, which is nothing but the impulse, is the change in momentum. So PA dash minus PA. Again, B on A will be P dash B minus PB. Same interval has been taken because they collide for same interval. Now we know by third law, FAB will be equal to minus FBA, that is the forces will be equal and opposite for both. In FAB put this and FBA put this. Now rearrange, that is take PA dash and P dash B here, means you have to take this on the left hand side, this on the right hand side. So P dash A plus P dash B equal to PA plus PB. What this is showing is the total momentum, final momentum of the isolated system is equal to the initial momentum. And this is even true for elastic as well as inelastic collision. So in elastic collision, there is a second condition, that the total kinetic energy that we'll talk about of the system will be equal to the total final kinetic energy that we are going to see in the later discussions. So there is equilibrium of particle, that is when no net external force, that is zero net external force is acting, this points to equilibrium of a particle. We have first law, this means that the particle will either be at rest or in uniform motion. So if two forces F1 and F2, they are acting on a particle, F1 will be equal to minus F2. That means that two forces on the particle must be equal and opposite, which is our one more law. Even if you have more forces, that is F1, F2, F3, these are concurrent forces, the vector sum of these three forces is 0. So F1 plus F2 plus F3 is equal to 0. So if this is F1, this is F2, they are equal and opposite. If you take three forces, say F1, F2, F3, then F3 will be, if we can just rearrange this, F1 and F2, this will be F3. So what we are saying here is the resultant of any two forces, say F1 and F2, which is obtained by, of course, the parallelogram law, must be equal and opposite to F3. So we have three forces, and you see we have taken a triangle, the vector arrows, these are making some, the sense of where it is acting, and the result can be generalized to any number of forces. You can take from Fn to F1 to Fn, and can be any number of forces. And because there are three forces, we have a triangle, you can take n side polygon for Fn. Also the x component, the y component, the z component has to be 0 like this. A mass of 6 kg is suspended by a rope of length 2 meter from the ceiling. So this is from here to here it is 1 meter, from here to here it is 1 meter. So in all it is 2 meter. A force of 50 Newton in the horizontal direction, this is force in horizontal direction, is applied at the midpoint of the rope. So what is the angle of the rope, or this angle the rope makes with the vertical in equilibrium? So this angle we have to find out. We have to neglect the mass of the rope. In this case, we make free body diagram. So what are the free body diagram? There are two things which are happening here. For this body, okay, what is happening, and at this point what is happening. So these are 2 points which we need to concern or consider. First, let us make the free body of this part. So we have this weight, 60 Newton is down, means acting downwards, and tension T2 is acting upwards. In this case, we have 50 Newton as said in the question. Of course, it has T2 also, so T2 will be like this, and there is T1, so this will be T1. So this is 50, T2, T1. Let us take for this one. So T2 will be equivalent to 60 Newton by the equilibrium of the weight. So T2 is simply 6 into 10. 10 is gravity. So it will be, tension will be, T2 will be 60 Newton. Let us consider this equilibrium of point P under the action of three forces. So there are three forces, T1, T2 and 50. The horizontal and vertical component of the resultant force, because this is at rest, so it has to vanish separately. So T1, this component will be T1 cos theta and this component will be T1 sin theta. So T1 sin theta will be equal to 50 and T1 cos theta will be equal to T2. So what we have done here, T2 we have just found out it is 60 Newton, so just place it here. T1 is 50 Newton, it is given in the question. Let us divide these two. Tan theta will be 5 by 6, theta will be tan inverse of 5 by 6, so this angle will be 40 degree. Common forces in mechanics. So there are certain forces which are talked about, but the gravitational force or the magnetic force, these are also certain force which come into picture. So there are certain forces which are contact forces, there are certain forces which are not contact forces. That means the gravitational force is not a contact force. But when you are talking about a book resting on a table, or say a system of rigid bodies connected by rod, hinges and other supports, there are contact forces. And the component of contact force normal to the surface is called normal reaction. So any body which is placed, say a book is placed here, so if this is mg, there will be a contact force. You can also say that in water also, fluid also, you will find it. If you press something inside this water, say a cork, there will be an equal and opposite forces of force, resultant force, and that is the buoyant force. The upward force applied by the liquid or fluid is the buoyant force. The air resistance, viscous force, they are also the contact forces. And two other common forces, as you see here, is the tension in the string, the force due to this spring, and of course this is given by F equal to minus kx. Why? If we have this mg, say some force, this is some kx, and kx is x is the displacement of this spring, so compression is also a part being played. And these are all the type of different forces which may act. As I said, gravitational force and electrical force, these are also relevant to the mechanics part. But you will be surprised when we are talking about uncharged and non-magnetic bodies in mechanics. In this case, see, the different forces, when we are talking about electric forces, they come from some charging and uncharging. So we will try to talk about the macroscopic scale, not to the internal level like electrons, etc., nuclei and electrons. Friction. What is friction? That is how we walk. So the force of gravity, as we saw, that something is placed on the table, the force of the gravity we have, and why this body is at rest, why it is not moving, there is some force, something which is holding this body. Of course the gravity is there, there is a force also, but when you push it, very mild force if you apply, then you see that it is not going to move. Why it is not moving with mild force? You are applying some force, it is mild force, but the net force is 0. But when you apply certain more force, this is going to move. So when a body is at rest and there is a force applied and this is not moving, this force, which is, say, impending force, or the force which is stopping this to move, not allowing it to move, this is called Fs, or static force. But when you press with some more energy, this is going to move. So the force which is now impending or trying to resist this your energy or this movement of this body, is Fk. S is for static, and this F sub k and F sub k. So this S and K stands for static and kinetic. So static and sliding forces you are seeing here. Fs is parallel to the surface of the body in contact with the table. This is frictional force, or you can simply call it as a friction. And there is a subscript, as I said, that when it is moving it will be Fk. So these are the impending motion of the body in this case, which is opposed by the static friction. And when the external force exceeds the maximum limit of static friction, the body begins to move. And once the body is in motion, it is subjected to sliding or kinetic friction, which is Fk, which is again opposing the movement. And this kinetic friction Fk is generally less than Fs. As you see here, Fs, you are applying force but it is not moving, very little force. When you are applying more force, it has started moving. Now the Fk becomes less than Fs generally. And when there is no force applied, as I said, there is no friction, means no static friction. It comes into play when you actually apply a force. So this Fs is what it is opposing. So that is why we are calling it as a static friction. The body is kept at rest. This is the impending motion. This Fs max is at what point you actually push it and it starts moving. So Fs max is that static friction max, and this force is the maximum force that can hold that body, beyond which if you apply the opposite force, the body is going to move. So Fs max is first of all, it is independent of the area of the contact, but it varies with the normal force. So this is directly proportional to the n, that is the normal force. So we have this mu s. You can say this Fs is directly proportional to n. So this proportionality sign can be changed to mu s. This is the constant of proportionality, and we call this mu s is the coefficient of static friction. And the law of static friction, this can easily be written as Fs, because this is about maximum. When you talk about normal Fs, that is F sub s, that is static friction, it is less than or equal to mu s n. When it becomes equal, that means you are trying to judge the maximum static force. So if the force you apply, or the applied force, exceed this Fs max, the body is going to slide. It starts moving, below which it is not going to move. And the friction force that is opposing the motion is called the kinetic or sliding friction, which is known as, which we represent by Fk. And again, the kinetic friction is also independent of the area of the contact, and nearly they are independent of the velocity also. Now what Fk has, Fk is similar to the Fs, so it is also directly proportional to the normal force. So we have this mu k as the proportionality constant, and this is known as the coefficient of kinetic friction. So if we apply, say, some F force, let us see here. If we apply some F force, this is Fk acting on the other side. So F minus Fk will be equal to what? Ma. The resultant force will be equal to mass into acceleration. So acceleration will be F minus Fk by m, which is given by this. And if we have a constant velocity, this acceleration will be 0. This whole will be 0. So F minus Fk will be eventually be 0. So F will be equal to Fk. Okay. And if the applied force on the body is removed, the acceleration is minus Fk by m, because the body is going to eventually stop. So the laws of friction, which we just saw, they do not have this one and this one. They do not have any fundamental. They are not fundamental laws like those for gravitational and electrical and magnetic forces. They are just empirical relation that we will be using to solve our problems. So when two bodies are in contact, each experiences a contact force by other, and friction, as we said, by definition, the component of the contact force which is parallel to the surface. Again, if this body is kept, or some car is moving, some sort of body is there, so this contact This is the friction which is acting on it. This is a relative motion basically, because the frictional forces is opposing. Okay. If a box is lying in the compartment of a train which is accelerating, we have friction. So all these are in the examples, these are all the examples of Fs and Fk. Let us take an example, you will understand it better. Determine the maximum acceleration of train in which a box lying on its floor will remain stationary, given that the coefficient of static friction between the box and the train floor is 0.15. In this case, the acceleration of the box is due to the static friction. Okay. So force is what? M into A. So what this will be? We know that Fs is less than equal to mu s n. This already we know, this expression. N is what? This is normal force. So if this is the normal force, what will be there? That will be equal to mg. Let us put mg in this case. So ma will be equal to mu s into mg. Gets cancelled out. A will be equal to, or A will less than equal to mu s into g. Mu s is also given, g is also given. Just multiply them. This will be 1.5 meter per second square. In this figure, a mass of 4 kg rests on a horizontal plane. So it is resting. It is not moving. The plane is gradually inclined until at an angle 15 degree. With the horizontal, the mass just begin to slide. So initially it was like this, then it was taken up this one. So it goes like this. When it reaches this 15 degree, the mass would slide. What is the coefficient of static friction between the block and the surface? So we have certain component we have to make here. The forces acting on a block of a mass m at rest on an inclined plane are what? First of all, we have this weight mg. There is a normal force. Normal force always act normal to the surface. So if this is a surface, this will be the normal force. Okay. Then we have this Fs. This is also acting, which is the impending force, static friction force. So because it is at equilibrium, the resultant force or the resultant of these force must be 0. So if this is mg, if this is theta, this will also be theta, by trigonometry. If this is mg, this will be mg cos theta component, this will be mg sin theta component. So if these are all in equilibrium, so Fs has to be equal to mg sin theta and has to be equal to mg cos theta, which is done here. But as we increase the theta, this self-adjusting frictional force Fs increases until theta is equal to theta max. And theta max is what? It is given that theta max, the maximum angle is 15 degree. So this Fs max is, we know that Fs max is mu s into n. This tan theta max is equal to mu. We just have to divide these two, this one and this one. And theta max will be tan inverse mu s. Okay. When theta becomes just more than this theta becomes more than just more than theta max, there will be a small net force on the block and this is going to slide. And theta max depend only on this mu s and it is independent of the mass. So what will be the theta max? It is given as 15 degree. So you can always find mu s by putting 15 degree here. This is equal to 0.27. What is the acceleration of a block and the trolley system shown in this figure? If the coefficient of kinetic friction Fk between the trolley and the surface is 0.04. And what is the tension in this string? We have to take G equal to 10 meter per second square. So this is the whole scenario. You have a trolley system. This is a block, and we have a trolley system here. This is a trolley. So we have, when it is moving, we have Fk as the opposing force. That is the surface force because it is moving. So we have Fk. This is 20 kg. This is tension, and the same tension will be here because this is a pulley. 30 Newton or 30 Newton will be the force. That is because of gravity. So let us make the free body diagram of these 2 points. First we'll make this one. So we have a tension here. So T tension is given like this. And of course 30 Newton is acting downwards. So T minus 30 is the actual force which will give you mass into acceleration. Mass is 3 kg. So 30 minus T equal to 3 into A. In this case, we have tension here, which is this one. Fk is opposing, and this is 20 kg. So this T minus Fk will be equal to m into A. Mass in this case is 20 kg. So T minus Fk will be 20A. And we know for this Fk, what will be the Fk? Fk will be equal to mu k into n. This we already know. Mu k is given as 0.04. Put it here. So n will be simply 20 into 10. That is 200 Newton. Now, put these value Fk we have found out in this, and this gives you another scenario. We have to just solve these two equations. We get acceleration and T. What is the rolling friction? A body, see, if you have a ring or a sphere, if you just roll them, they goes for long, means they travel for long, or they are in motion for a considerable amount of time. In case you just press or give motion to this body, it is going to just stop here, but the sphere or a ring is going to go long. Why this scenario is? Because the friction force which is acting here is less. The actual area which is touching the surface is less because it is moving, but in this case it is long. And as we said, the friction is independent of the area, but because the surface which is in contact is very less. I hope you got the idea. So that is why because you know, these friction forces, movement friction forces, they are very difficult to handle. Means the machines which are acting, these motors are actually acting against the friction forces only. But there are certain ways in which we can solve it. We can put, these are the ways of reducing friction. We can add the ball bearing, which is placed between moving parts of a machine. We can have some compressed cushion of air between surfaces, which gives rise to, or we can minimize this friction. So this is one more part of the discussion we are having. We'll be taking one more. So till then, thank you so much and take care of yourself.